Alright guys, today we're going to start looking at continuity. So continuity is actually going to involve limits a little bit. But to start off, just the very basics, let's look at these top three graphs. And if you guys look here, I think you guys can figure out just by looking at the pictures which of these three graphs is continuous for everything that's shown. If you look at this first graph is completely continuous for the entire interval that's shown here. Because if I were to trace this entire graph, I don't need to pick up my pencil. So that's the easiest way to tell if a graph is going to be continuous when you're looking at the picture. Obviously this rational function here is not continuous, because if I follow this graph, the only way to get to the next part is if I pick up my pen and then I move to the next part. So that graph is discontinuous, and it's discontinuous when x is equal to 0 because of that vertical asymptote. Then again, if you look over here in this next one, it's almost completely continuous. The problem is that open circle there has to stop and move my pen, so it's not continuous as well. And again, I don't have any points listed, but let's just say that's discontinuous when x equals -2. Now what you're going to look at down there at the bottom, that's the exact definition of what makes a function continuous at a certain point. So we say that a function is continuous when x is equal to some value if, first of all, the first step is the function must be defined at that value. Okay, so let's say, for example, I have a function that looks like this. Now if you look, that function isn't defined at that value. Okay, so at 2, when x is equal to 2, there isn't anything, it's not defined. So this function is discontinuous when x is equal to 2. It's continuous everywhere else except for that one point because of that open circle, because that value is not defined. All right, the next one is, it says that the limit as x approaches c of that function has to exist. Okay, so let's say I had a function that looked like this. Alright, so if you look at this function, it's defined at the value x equals -2, but the limit does not exist at x equals -2. So this function is also discontinuous when x equals -2, and it's for a different reason. Again, the value does exist, the value is defined, however that limit doesn't exist because you can see at -2, my left side and right side are approaching two different values, and we learned a couple days ago that that can't happen. Now the last thing that's true, it says if that limit exists, and if that function is defined, those two values need to be equal. Alright, so we're going to look at one last example to see when that wouldn't be the case. So what I'm going to do is I'm going to look at this picture up here at the top. And I'm going to go ahead and mark some points on there. Let's say that's here, and then this is here. Alright, so if you look, let's say specifically we're going to look at when x is equal to -2. We're going to see if this graph is continuous. Now by looking at the graph, you guys can tell it probably isn't continuous at that point. But what this is saying is, let's find what the limit is. So let's find the limit as x approaches -2 on this graph. Okay, I actually can find that value. My limit as x approaches -2 of that function is the y value of 2, because both sides of my graph are approaching that open circle that has a y value of 2. Now, I also can evaluate this function. If I wanted to, I could evaluate that function at -2, because it actually is defined. It's defined at that closed circle down there that we're going to say, I didn't draw it very well, let's just say that y value is -3. So both of those first two statements are true. F of c is defined, it's equal to -3, and the limit as x approaches -2 also exists, it's 2. But this invalidates that third statement, which says that those two numbers have to be equal. And because those two numbers are not equal, x is discontinuous when x is equal to -2. And I am out of space, but that word would be discontinuous. Alright, so we're just going to look at a couple of examples here to figure out whether or not some of these functions are going to be continuous. Now this very first one is a normal polynomial here. I have the function x to the third power plus 1. And if you guys think about what that graph is going to look like, that takes your cubic parent function and just shifts it up 1. Okay, so if you think about it, that graph is just going to look something like that. And you know those functions that look like that, they're not really discontinuous anywhere. I can easily find all three of those statements. The first one is f of 2 has to exist. Well, we can find that. I can take 2, plug it into my equation, and I get 9. I also know if I try to find that limit, I'm going to get the same answer, because all I'm going to do is I'm going to plug in 2, and I'm going to get 9. And because 9 is equal to 9, this follows all three of the rules we just looked at, which means this function is continuous at x equals 2. In fact, that function is going to be continuous everywhere. And what's going to make this a little bit easier on you guys is all polynomials and even sine and cosine, and also your radical functions like the square root of x. All of those types of functions are going to be continuous everywhere in their domain. And the reason I'm saying their domain is if you think about the function y equals the square root of x, that function is continuous everywhere. However, we know that that function isn't going to have negative x values because it can't take negative square roots. So everywhere that function actually is, which starts at 0 and goes on, it's continuous from there on. Alright, so now let's look at this next function. This one is obviously a rational function, okay, so it's not necessarily going to be continuous everywhere. So specifically, I want to know, is this function continuous at x equals 3? So the first thing I'm going to do is I'm going to try to evaluate this function when x is equal to 3. So I'm going to start with my first test, and my first test is to evaluate, is f of 3 defined? So I'm going to plug in 3 to my original equation. So I'll have 9 minus 3 minus 6 divided by 9 minus 6 minus 3. And you know what's going to happen here. I'm going to get 0 over 0. Now, while that's indeterminate for a limit, we can still find this limit maybe. I cannot evaluate this function. This function does not have a value at 3. So because this is not defined, then this function is not continuous at x equals 3. Now what we could do in this function, if we wanted to look at it a little farther, I'm going to go ahead and factor this function out. So this function is going to factor into, on the top, I'm going to have x minus 3 and x plus 2. And then at the bottom, it's going to factor into x minus 3 and x plus 1. And hopefully you guys remember a little bit about rational functions. We're going to get a couple of things here. My x minus 3 functions cancel out. So if you remember at 3, what I'm actually going to have there is a whole. Or what we're going to call now, because we're talking about continuity, that is a removable discontinuity. Then if you look at that remaining function, the remaining function still isn't continuous everywhere, because the bottom of that remaining function still has something that could divide by 0. So that function also would still be discontinuous at x equals negative 1, because at x equals negative 1, we're going to have a vertical asymptote. So that function is actually discontinuous in 2 places, and actually for 2 different reasons. So there's 3 types of discontinuity that we're going to look at. The first one is going to be a removable discontinuity, which is just a hole in my graph. And we've already talked about those when we did rational functions. Those occur anytime I cancel out a factor. Right, the next kind of discontinuity, wow, I'm having trouble saying, that's a vertical asymptote, just like what we just did. So the vertical asymptote is after we've canceled anything out, whatever makes the bottom equal 0. And then we're also going to see some breaks or some jumps. And those are going to happen mostly in piecewise functions. But an example of that we've actually already seen on this. A break or a jump would be if I have a graph that looks something like this. And those are places where that limit does not exist, whether or not that function is defined at that place. What makes the vertical asymptote different on a graph, remember the asymptotes is specifically where your graph is trending towards infinity or towards negative infinity. Whereas on your break, your graph isn't necessarily going towards infinity, it's stopping at a point. It's just not connected. And then the hole, what makes the hole even more different is it's just an open circle and your graph keeps going. You can still find the limit when you have a removal discontinuity. And in fact, it's the only one of those that we actually can find that limit still. Alright, so we're going to look at two last examples, and these are both going to be piecewise functions. So sometimes these are a little bit more difficult, so we're going to take these a little bit slower. So the first function here, it tells me I have a certain graph when my function is greater than 3, and I have another graph when my function is less than 3. So in order to find if this is continuous, I'm going to follow those same 3 steps. Those same 3 things need to be true that I've been doing all along. So the first step I have on here that I need to figure out is, number 1, is f of 3 defined on this function? So if I look, this function is equal to 3 at that bottom function because that's when x is less than or equal to 3. So yes, that function has a point where it's 3, so what I'm going to do is I'm going to take 3 and plug it into that equation. So negative 2 times 3 plus 2, and that gives me a value of negative 4. So that first statement holds true. This function is defined at that point. Now we need to follow the next statement, and the next statement says, does that limit exist? So I need to figure out, does the limit, as x approaches 3, of f of x, of that function right there, does that limit exist? So if you guys remember, in order to find that limit on a piecewise function, I need to make sure the left side and right side are doing the same thing. So I'm going to start with the right side. The right side is going to be when x is greater than 3. So I'm going to use the function x minus 2. So if I take 3 and substitute it into the right side, I get 1. Now I'm going to look at the left side. So the left side is going to be true when x is less than 3. So to get my left side, I'm going to use the function negative 2x plus 2, which I've already used, I just did it down there, and I'm going to substitute 3 into that equation, and I'm going to get negative 4. So if you look, my left side and my right side are doing two different things, and we know that that means that that limit does not exist. And because that limit does not exist, this function is not continuous at x equals 3. Alright, now the last one we're going to look at again is another piecewise function, and we're going to see if this one's continuous at 3, and we're going to do it the same way. We're going to follow those same steps and those same tests. So the first thing that needs to be true is f of 5 defined? Can I get a value by plugging in 5? Of those two piecewise functions, I'm going to use the bottom one because x is less than or equal to this function at 5. So I'm going to use 5 squared minus 16. So 25 minus 16 is going to give me 9. So yes, that first one is true. That function is defined. That value is 9. Second thing I'm going to do is I'm going to find the limit. So the limit as x approaches 5 of that equation. I'm going to do it the same way. I'm going to check the left side and I'm going to check the right side. So I'm going to start with the left side. The left side is going to be everywhere that it's less than, which is my bottom equation. So the left side I'm going to do 5 squared minus 16, which is still 9. Then I'm going to do the right side, and the right side is everywhere where it's greater. And it's greater at 2x minus 1. So I'm going to do 2 times 5 minus 1, and I get the value of 9. So both my left side and my right side are approaching 9, which means that limit does exist, and that limit is equal to 9. So the second one is also true. So now my last step down here, my third step, needs to be, is it true that f of 5 is equivalent, it looks like a 6, is f of 5 equivalent to the limit as x approaches 5 of f of x? So really what that question is asking is, does step 1 equal step 2? And yes, that's true, because 9 is equal to 9. So since all three cases right there are true, this function is continuous at the value x equals 5.